Welcome to Cosmic Sedation, your peaceful journey through the stars. Tonight, we explore why the cosmic microwave background radiation fills every corner of space, a whisper from the Big Bang. This ancient echo tells us the story of our universe's birth. If you enjoy this kind of cosmic calm, consider subscribing and liking for more serene stargazing nights ahead. As the stars align, let's begin our quiet voyage through time and space. At -270 degrees Celsius, the cosmic microwave background radiation, CMB, fills every corner of space, a temperature so cold that it approaches absolute zero. This radiation is not simply a leftover echo from the Big Bang. It is an imprint of the universe's earliest moments, stretching across 13.8 billion years. Each photon in this radiation has been traveling for almost as long as time itself, yet they have cooled significantly due to the ongoing expansion of the universe. The wavelengths of these photons have stretched by a factor of 1,000 since their emission, transforming high-energy gamma rays into microwave light. For context, if you were to place your hand in an environment at -230 degrees Celsius, it would freeze instantly, yet this is still warmer than the CMB. The expansion of space itself stretches these wavelengths, cooling the photons over time, a phenomenon known as redshift. Imagine a rubber band stretched between 2 points. As the distance increases, the band becomes longer and thinner. Similarly, the fabric of spacetime expands, elongating the paths that light must travel. This process has been ongoing for billions of years, gradually reducing the energy of these photons. The CMB's temperature today is -270 degrees Celsius, a stark contrast to its initial 3,000 degree Kelvin at the moment of photon decoupling. Remarkably, this cooling effect means that what was once a blinding flash of light has become an almost imperceptible whisper in the cosmic background. This expansion-induced cooling is a testament to how space itself can alter the fundamental nature of light. To understand the scale of this phenomenon, consider that when these photons were first emitted, they had wavelengths similar to those of visible light. Today, their average wavelength has stretched to about 1 millimeter, placing them firmly in the microwave region of the electromagnetic spectrum. This shift is not just a change in color, but also a profound alteration in how we interact with this radiation. The CMB's journey through time and space means that it now interacts primarily with radio telescopes rather than human eyes. In fact, if you were to tune an old television set between channels, the static you see is partly due to these ancient photons. This connection between the Big Bang and your living room television is a humbling reminder of how deeply intertwined our universe's history is with everyday life. The expansion of space continues to stretch these wavelengths even today, meaning that the CMB will continue cooling over time. In another trillion years, the temperature could drop below -271 degrees Celsius, approaching absolute zero, but never quite reaching it due to quantum fluctuations. This gradual cooling process underscores the vastness and age of our universe. While this may seem inconsequential on a human timescale, consider that the entire observable universe is expanding at an accelerating rate. The CMB's cooling is not just a passive observation, but also a dynamic process that reflects the ongoing expansion of space itself. It serves as a constant reminder of how the universe evolves over time, from its fiery birth to this cold and diffuse state. The CMB provides a unique window into the early universe, offering insights into the conditions shortly after the Big Bang. By studying these photons, scientists can infer details about cosmic inflation, dark matter, and even the distribution of galaxies today. The cooling process due to expansion is not just a passive phenomenon. It actively shapes our understanding of cosmology. For instance, the slight variations in temperature across different regions of the CMB, measured at 1 part in 100,000, are crucial for understanding how structures like galaxies and clusters formed over time. These minute fluctuations are the seeds from which all cosmic structure grew, a process that continues to unfold even as the CMB itself cools. The ongoing expansion of space also means that distant regions of the universe are moving away from us at an accelerating rate. This expansion stretches the wavelengths of light emitted by these far-off galaxies, causing their colors to shift toward redder frequencies, a phenomenon known as redshift. As a result, some photons will eventually travel so far and for such long periods that they will be stretched beyond our ability to detect them. The CMB is thus not just a relic from the past, but also a harbinger of what lies ahead, a universe where even the most distant light becomes increasingly difficult to observe. This process highlights the finite nature of our observable universe, while simultaneously offering a glimpse into its infinite potential. As we continue to study these ancient photons, we are not only uncovering secrets about the birth of our cosmos, but also peering into the future of its expansion and eventual cooling. The temperature fluctuations within the cosmic microwave background radiation, CMB, are so minute that they vary by less than 1 part in 100,000 across the entire observable universe. These variations, at a scale of mere microkelvins, represent the earliest seeds from which galaxies and stars would eventually form. Yet, these tiny differences span 14 billion light-years, echoing the conditions just 380,000 years after the Big Bang. Imagine if every grain of sand on Earth represented 1 part in 100,000. This is akin to measuring an infinitesimal fluctuation across cosmic distances. To grasp the scale, consider that these minute temperature variations are responsible for the structure we see today, clusters of galaxies and voids where nothing exists. The CMB's fluctuations trace back to quantum fluctuations in the early universe, magnified by inflation. In essence, what you perceive as a uniform glow is actually a detailed map of the cosmos at its infancy. If your eye could detect this radiation, it would see not just emptiness, but an intricate web of density variations. These variations are so consistent that they have been mapped with extraordinary precision, revealing patterns that align with our understanding of how the universe evolved. Each point in the CMB represents a snapshot of what the universe looked like at 380,000 years old. This age corresponds to just 0.026% of the current estimated age of the universe, 13.7 billion years. The light from these fluctuations has been traveling through space for nearly all that time, stretching as the universe expands. For context, if you were born at the moment this radiation began its journey, you would now be older than most known stars in our galaxy. This ancient light is a direct connection to the birth of the cosmos, unaltered by any intervening events. The CMB's temperature fluctuations are not just random noise. They follow a specific pattern that cosmologists have decoded through decades of study. These patterns provide evidence for the theory of cosmic inflation, the rapid expansion of space in the first fractions of a second after the Big Bang. This brief period smoothed out most irregularities, but quantum fluctuations left behind small seeds of density variations. These seeds grew into the galaxies and galaxy clusters we observe today. The precision with which these patterns are measured is remarkable. They align perfectly with predictions from inflationary theory, suggesting that our universe began in a state of extreme uniformity. Consider this. If you could place yourself at any point in space far beyond Earth's atmosphere, the CMB would appear as an almost uniformly cold and dim glow. However, the precision instruments we use to measure it reveal its subtle variations. These fluctuations are so small that they challenge our ability to detect them on Earth. Yet, their existence is crucial for understanding how matter clumped together to form galaxies. The CMB's temperature differences are akin to ripples in a pond, each one signaling where stars and planets would eventually coalesce. The CMB provides not only a snapshot of the early universe, but also clues about its future. By studying these minute variations, scientists can predict how structures will continue to evolve over time. In billions of years, galaxies may merge into larger clusters or even superclusters, influenced by the initial density fluctuations seen in the CMB. The radiation itself continues to expand with the universe, stretching further and cooling more as it travels. Yet, its legacy remains, a blueprint for all that exists today and will exist tomorrow. This ancient light is both a whisper from the Big Bang and a roadmap for understanding our cosmic neighborhood. Interstellar dust, composed of particles no larger than grains of sand, scatters and absorbs cosmic microwave background, CMB, radiation as it traverses through space. This interaction subtly alters the CMB's path and intensity. The CMB photons scatter off these tiny particles, a process known as Thomson scattering. Each time they collide, the energy is slightly redistributed. This effect is akin to how light bounces off a foggy window. The image becomes less clear but more diffuse. This phenomenon occurs on an astronomical scale, with each collision occurring across distances measured in light years. The cumulative impact of these interactions can shift the CMB's spectrum ever so slightly, introducing minute variations in temperature and intensity that astronomers must correct for to ensure accurate measurements. Yet, it is this very scattering that also allows us to map the distribution of dust throughout galaxies, revealing intricate patterns of star formation. As these photons from the early universe interact with interstellar dust, they undergo a transformation that connects our understanding of ancient events with contemporary observations. The CMB radiation, born just 380,000 years after the Big Bang, travels through time and space unimpeded until it encounters this cosmic debris. This interaction serves as a bridge between two epochs, the primordial universe and the present-day cosmos. It's a reminder that even the faintest glow from the dawn of time is affected by the material present in our galaxy today. The interstellar dust not only alters the CMB, but also provides clues about its journey through space. By examining how much the radiation has been scattered, scientists can estimate the density and distribution of dust along various lines of sight. This information helps refine models of star formation and galactic evolution. In some regions, where dense clouds of gas and dust are present, the CMB is significantly dimmed. These areas appear as cold spots in temperature maps, hinting at structures that have yet to form stars, but will do so over billions of years. Remarkably, this scattering process also reveals the presence of an unexpected phenomenon: polarized light from the CMB. When photons scatter off charged particles in interstellar dust, they can become polarized, meaning their electric fields oscillate preferentially along one direction. This polarization is a faint but crucial signature that carries information about the conditions at recombination, the epoch when electrons and protons first combined into neutral atoms, allowing light to travel freely through space for the first time. Detecting this subtle signal requires instruments sensitive enough to distinguish it from background noise. Yet it provides invaluable insights into the early universe's magnetic fields. Intriguingly, these interactions between CMB radiation and interstellar dust also have implications for future cosmological studies. As technology improves, astronomers will be able to map these scattering effects with greater precision, potentially uncovering new details about both the early universe and our own galaxy's structure. The subtle distortions caused by dust provide a window into conditions that existed billions of years ago, offering glimpses of epochs long past. This interplay between ancient radiation and modern-day material underscores how deeply interconnected different scales of the cosmos truly are. Consider this. On a clear night in rural America, where the sky is unobstructed by city lights, you might observe approximately 2,500 stars visible to the naked eye. Each star emits light that travels vast distances across galaxies before reaching your eyes. Now, contrast this with the cosmic microwave background radiation, CMB, which fills every cubic meter of space uniformly. The CMB's energy density is about 4 times less than that of a quiet rural night sky's starlight. Yet it permeates all of space without any visible source. The paradox lies in how something so faint can be everywhere at once. While the starlight originates from individual burning stars scattered across vast distances, the CMB arises from a time when the universe was a mere 380,000 years old, immediately after it had cooled enough for protons and electrons to form neutral hydrogen atoms, allowing light to travel freely through space for the first time. This radiation is not just faint, it is an imprint of the early universe's temperature variations, each pixel in our observations representing a tiny fraction of what would have been an unimaginably hot and dense state. The CMB's presence today can be likened to water vapor filling a room evenly after boiling has stopped. In this analogy, The stars are like localized condensation on windows, visible, but not filling the entire space uniformly. The CMB's uniformity across billions of light years suggests that when it was emitted, the universe was astonishingly homogeneous on large scales. This uniformity challenges our perception of randomness and chaos in nature, hinting at a simpler, more ordered past. In human terms, consider how faint this radiation is. If you were to convert its energy into heat, it would feel colder than the coldest place ever recorded on Earth, the highlands of Antarctica. Yet this coldness is not just an absence of warmth, it's a remnant of the Big Bang itself, preserved in every direction we look. The CMB has been traveling through space for billions of years, gradually cooling as the universe expands. It's as if time itself leaves imprints on light. The CMB's energy is so diffuse that its effect on any object or person is negligible. However, it plays a crucial role in cosmology by providing a snapshot of the early universe. By analyzing these ancient photons, scientists can infer properties about the universe's expansion rate and composition. This radiation has been fundamental in confirming theories like inflation, wherein the universe underwent an exponential expansion in its earliest moments. Despite being invisible to our eyes, the CMB is detectable by specialized instruments designed to pick up microwave frequencies. These instruments have revealed subtle temperature variations across the sky that are less than a millionth of a degree. Each variation corresponds to regions where matter was slightly denser or less dense billions of years ago, leading to the formation of galaxies and clusters we see today. This faint whisper from the Big Bang underscores the universe's intricate balance between order and chaos, guiding our understanding of cosmic evolution. In the distant reaches of the cosmos, each photon from the cosmic microwave background radiation, CMB, has been traveling for nearly 13.8 billion years. These photons originated in the earliest moments after the Big Bang, when temperatures soared to over 1 trillion degrees Celsius. Now, they fill every corner of space with an eerie glow, their energy diluted by the expansion of the universe. This radiation, once searing hot, has been stretched and cooled by cosmic expansion, akin to how the sound waves from a distant siren grow fainter as it moves away. The CMB we detect today is at a temperature just 2.7 degrees above absolute zero, a paradoxical coldness for light born in the universe's hottest moment. Yet this cooling has not diminished its significance. Instead, it preserves the earliest snapshot of our cosmos, etched in the subtle variations of temperature. The redshift effect plays a pivotal role in this chilling transformation. As space expands, wavelengths stretch and shift towards longer frequencies, hence the term redshift. This phenomenon is so pronounced that what began as high-energy gamma rays has been stretched into microwave radiation detectable by radio telescopes. Imagine light from your childhood bedroom dimming over billions of years until it becomes imperceptible to human eyes. These photons are not just remnants of a fiery past. They also serve as witnesses to the universe's ongoing expansion. Each photon's journey across vast distances provides a timeline for cosmic history, marking epochs when galaxies formed and evolved. Were we able to observe this radiation at its original energy levels, It would have been blindingly intense, enough to melt metals were our eyes capable of capturing such high-energy light. The CMB's uniformity is remarkable given the chaotic conditions following the Big Bang. Yet slight temperature differences exist, varying by only a few parts per million across the sky. These tiny fluctuations are crucial. They represent the seeds from which galaxies and clusters grew. They hint at subtle density variations in the early universe, where quantum fluctuations were magnified to cosmic scales, sowing the seeds for all structure we see today. While these photons traverse the cosmos with an eternal presence, their journey is far from static. Each photon interacts minimally with matter as it travels through space, occasionally scattering off electrons or atoms, but rarely changing direction significantly. This means they carry a direct message from the universe's infancy, undisturbed by intervening events. In contrast to transient celestial phenomena like supernovae, which last mere moments before fading into darkness, CMB photons persistently illuminate the cosmos with their ancient light. The cosmic microwave background radiation, CMB, not only fills every corner of space, but also serves as a cosmic thermometer, its temperature meticulously charting the universe's cooling over billions of years. Every square meter in deep space receives roughly 400 watts per square meter from this radiation, enough to provide a constant, albeit minuscule, heat source across the vast expanses of interstellar and intergalactic voids. Yet, despite this pervasive presence, it remains unnoticed by human senses due to its microwave frequency range. This radiation is so faint that if you were to listen to it using a radio designed for FM broadcasts, it would sound like nothing but static. Yet this static contains the universe's most profound secrets. The CMB's journey from the early universe to today has been one of relentless expansion and cooling. Its photons have been stretched by the fabric of space itself, their wavelengths elongated as if they were part of a cosmic accordion being played out over time. This redshift is so pronounced that what once would have been felt as scorching heat now feels like an imperceptibly cold whisper against the backdrop of deep space. Remarkably, this cooling effect has not diminished the CMB's utility for cosmologists. The minute temperature differences across its surface offer a precise map of the early universe's structure, like ripples in a pond that reveal hidden rocks beneath the water. These variations are so subtle that they represent less than 1 part in 100,000 of the average temperature. Yet, it is through these tiny fluctuations that scientists can infer the density and distribution of matter in the early universe. Imagine for a moment you could perceive the universe in microwave frequencies, as if your senses had been recalibrated to detect this ancient light that fills space. The cosmic microwave background radiation, CMB, permeates everywhere, its radiation pressure a constant but imperceptible presence against your skin. At -270 degrees Celsius, it is so cold that molecules almost cease their motion, yet it remains the most uniform temperature across the entire universe. If you could feel this radiation, it would be like standing in a perfectly still, uniformly cool room. No breeze, no variation, only an unchanging chill. This radiation, born from the Big Bang and stretched thin by the expansion of space itself, is older than any star or galaxy. Every square meter of your skin would receive about 1 photon per second at microwave frequencies, a gentle touch from the dawn of time. This seemingly insignificant energy carries within it the seeds of cosmic structure, minute temperature differences that grew into clusters of galaxies and vast voids. The CMB, though invisible to our eyes, is far more pervasive than any cloud or atmosphere on Earth. To your recalibrated senses, this radiation would not be uniform at all, but a symphony of minute variations in intensity. These fluctuations are the result of quantum fluctuations from the moment of the Big Bang, stretched over billions of light years into what we now observe as subtle temperature differences. Each variation is like a fingerprint left by the earliest moments of the universe, marking regions that would eventually become denser and form structures. If you could detect these variations, they would create an ever-present sensation of gentle pressure fluctuations across your body. The CMB radiation, while ancient, also interacts with matter in our galaxy, particularly dust clouds and gas. As it passes through these dense regions, the photons scatter off electrons, a process that slightly alters their path and energy level. This scattering is akin to how light bends when it enters water or glass, only on an astronomical scale. These interactions mean that any journey you take through space would be accompanied by a subtle dance of particles, subtly altering the radiation's direction and intensity as it interacts with the interstellar environment. If your senses were attuned to microwave frequencies, the CMB would not only feel like a uniform coolness, but also carry an echo of time. Each photon has traveled for nearly 13.8 billion years to reach you, tracing paths through expanding space and cooling along the way. The radiation that touches you now began its journey when the universe was only about 380,000 years old, a cosmic infancy compared to today's age of approximately 13.8 billion years. This ancient light is a reminder of how much time has passed since the Big Bang and how vast the cosmos truly is. The CMB radiation also carries with it an imprint of the universe's early composition, hydrogen and helium atoms that formed just after the cosmic dark ages, when space was filled with plasma rather than stars. These elements are the building blocks for all matter in the universe today, including you. If your senses could perceive this radiation, each particle would be a messenger from an era before any stars shone or galaxies coalesced. The coolness of the CMB is thus not just a sensation, but a connection to the very origins of existence, reminding us of our place within the grand cosmic narrative. A billion years after the Big Bang, the universe was a place of near-uniform density, yet it harbored subtle variations in matter distribution that would eventually shape galaxies and clusters across the cosmos. These fluctuations were minuscule, only about 1 part in 100,000, but they set the stage for the formation of stars and galaxies long before the cosmic microwave background radiation, CMB, was emitted. Imagine these density differences as ripples on a pond, barely perceptible, but powerful enough to influence the flow of water around them. Remarkably, these tiny variations are not random, but instead follow precise patterns imprinted by quantum fluctuations in the earliest moments after the Big Bang. These seeds of structure were so minute that they would take billions of years and countless collisions of particles before their effects became visible as galaxies and superclusters. Yet, even at this early stage, gravity was already amplifying these tiny perturbations, turning them into the scaffolding upon which all cosmic structures would hang. The universe was a delicate balance of uniformity and subtle difference. The early universe's matter distribution wasn't static. It evolved over time as particles clumped together under the influence of gravity. This process is akin to watching ink diffuse in water, but in reverse, where instead of spreading out evenly, matter clusters into denser regions. These dense areas would eventually become galaxies, each containing billions of stars and trillions of planets. The density fluctuations grew exponentially over time, creating a cosmic web that spans the entire observable universe. By examining the CMB today, we can trace these ancient variations back to their origins. Each speckle in this radiation map corresponds to an area where matter was slightly more or less dense than average at that time. This allows us to peer into the past and understand how galaxies formed from these initial conditions. The fact that we can do so is a testament not just to the power of scientific observation, but also to the enduring nature of information carried through space on the backs of ancient photons. At this point in cosmic history, the universe was still much hotter than it is today, filled with a dense plasma of protons, electrons, and photons. Despite its extreme conditions, gravity was already at work, gently pulling matter together into denser regions. This process, known as gravitational collapse, would eventually lead to the formation of stars and galaxies. The density fluctuations acted like seeds, marking where these structures would grow over time. Understanding this early universe helps us appreciate how the cosmos has evolved from a uniform sea of particles into the intricate tapestry we see today. Each galaxy is a testament to those initial density variations, which have grown through complex processes spanning billions of years. As we study the CMB, we are not just observing the remnants of the Big Bang, but also glimpsing the birthplace of our own Milky Way and countless other galaxies. The density fluctuations in the early universe were like the first whispers of a grand symphony, their faint signals growing louder over time as they shaped the cosmic landscape. These variations, though imperceptible to human senses, played a crucial role in determining where matter would accumulate and form galaxies. The process was gradual. Over millions of years, gravity pulled particles together into denser regions, while less dense areas expanded outward. This delicate dance between attraction and repulsion set the stage for the intricate patterns we observe today in the cosmic web. At this early epoch, the universe was a sea of hydrogen and helium gas, interspersed with these tiny density variations. These fluctuations were not evenly distributed. Some regions had slightly more matter than others, creating a patchwork of varying densities across space. Each fluctuation acted as a gravitational well, attracting nearby particles and growing larger over time. This growth was exponential in nature. Once a region exceeded a critical mass, its gravitational pull increased significantly, drawing in even more material. The result was the formation of structures on an immense scale, from individual galaxies to vast galaxy clusters. These structures are still evolving today, with new stars being born and old ones dying within them. By studying the CMB, scientists can map out these initial density variations and trace their evolution into the large-scale structure we observe in the universe today. This connection between the microscopic fluctuations of the early universe and the macroscopic structures we see now is a profound demonstration of how small changes can lead to vast consequences over time. The universe's development from this delicate balance of uniformity and difference illustrates the intricate interplay of forces that govern cosmic evolution. In the far-flung reaches of deep time, billions upon billions of years hence, the cosmic microwave background radiation, CMB, will continue to permeate the cosmos, its signature fainter and more diffuse with each passing eon. Yet this ancient light is not static. It is an echo stretching across a universe that expands relentlessly. Each photon from the CMB has traveled for billions of years through the ever-stretching fabric of spacetime, their wavelengths now vastly elongated into microwave frequencies. This radiation, which once filled the early universe with its primordial glow, will become increasingly sparse as galaxies drift apart, leaving vast tracts of emptiness between them. As time unfolds and the universe continues to expand exponentially, the CMB photons will grow ever more isolated, their density decreasing at a rate that mirrors the accelerating expansion of space itself. This phenomenon is akin to watching ink diffuse in water, each drop spreading outwards until it becomes indistinguishable from its surroundings. The CMB's once uniform glow, now stretched thin across an unimaginably vast expanse, will eventually be diluted beyond recognition. Yet paradoxically, this very dilution ensures the CMB's eternal presence. It is a reminder of how even in the face of cosmic expansion, certain aspects endure. Imagine standing at the center of the universe as it expands, a thought experiment that defies physical reality but serves to illustrate the point. As you gaze outwards, each point on the horizon appears to recede from your view at an accelerating pace. In this vast arena, the CMB photons are like scattered grains in a field of expanding sand. They too will be stretched and separated. This expansion is not merely a spatial phenomenon, but also temporal. As the universe ages, the light's wavelength stretches, making it increasingly difficult to detect with current technologies, even though its presence remains constant. In another billion years or more, these ancient photons may no longer provide us with insights into the conditions of the early cosmos. Yet they will continue to travel through space, their energy levels dropping further as they are stretched by the expansion of the universe. The CMB's spectral line, a fingerprint of the Big Bang, will become so broad that it blends seamlessly into the background radiation of an increasingly cold and dark universe. This process is a testament to how even the most profound cosmic signatures can be overtaken by the sheer scale and duration of time. The expansion of space not only stretches the CMB, but also alters its temperature distribution. As galaxies move apart, the fluctuations in temperature that once defined the seeds of structure in the early universe will become increasingly subtle, nearly imperceptible against the backdrop of an ever-cooling cosmos. These minute variations are crucial to our understanding of how galaxies and clusters formed, yet their significance is fleeting when viewed from the perspective of cosmic time. The CMB's journey through the expanding universe mirrors a broader truth. Even the most enduring phenomena eventually succumb to the relentless passage of time. In this deep future, the universe will be a place where light itself becomes scarce, with stars and galaxies growing ever more distant and faint. Yet the CMB will persist as a relic of the past, its presence marking epochs long since faded from view. This radiation serves as a bridge between our observable universe and the unimaginable vastness beyond, both in space and time. As we lie here, contemplating these far-off times, it is worth reflecting on how even the faintest whisper from the Big Bang continues to shape our understanding of the cosmos, long after its origins have receded into memory. At an altitude of approximately 50 kilometers above Earth's surface, the cosmic microwave background, CMB, radiation interacts with atoms in our upper atmosphere. Here, photons from the Big Bang encounter nitrogen and oxygen molecules, initiating a series of subtle energy exchanges that ripple through this thin layer of air. Each photon carries an energy level so low it is imperceptible to human senses, yet these interactions are the foundation of a complex dance between ancient light and atmospheric particles. Remarkably, this interaction zone represents one of the few places where the CMB directly influences matter in the present universe. Far from being merely a passive observer, the radiation contributes to the excitation of atoms, subtly altering their energy states. This process underscores how the echoes of the Big Bang continue to shape the physical world around us, even billions of years after the event that set it all in motion. Yet, these interactions are fleeting and delicate, with each photon spending only a fraction of a second within this atmospheric layer before continuing its journey. As the CMB photons collide with atoms, they initiate a cascade of quantum events at temperatures just above absolute zero. This interaction triggers a brief state of ionization in some molecules, creating free electrons that scatter further light and heat. These processes are akin to the delicate balance maintained by ecosystems on Earth, where small shifts can have profound effects across entire systems. In this case, however, these shifts occur over astronomical scales and timescales far beyond human comprehension. The boundary layer where CMB meets atmosphere is also a site of ongoing scientific exploration. Satellites and ground-based instruments alike monitor the subtle fluctuations in energy levels as photons pass through. This monitoring reveals not only the state of our upper atmosphere, but also provides insights into the conditions of the early universe. The precision required to detect these interactions is extraordinary, with measurements often requiring instruments capable of detecting temperature changes smaller than a millionth of a degree. At this altitude, the CMB radiation bathes Earth in an unceasing stream that has been ongoing since the universe was approximately 380,000 years old. This radiation has traveled through space virtually unchanged for billions of years, only to interact with our atmosphere at its final destination. Each photon is a relic from the Big Bang, carrying information about the early cosmos imprinted on it when hydrogen atoms first formed. The interaction zone thus serves as an interface between the vastness of cosmic history and the immediate environment surrounding us. In this interaction layer, the CMB photons experience a brief period of attenuation before emerging back into space. This process is not uniform across all regions of Earth's atmosphere. Variations in atmospheric density can alter how these photons are scattered or absorbed. These differences create subtle patterns that scientists meticulously map to understand both cosmic history and local atmospheric conditions. The ongoing dance between the CMB and our upper atmosphere, therefore, is a dynamic and ever-evolving phenomenon, bridging the ancient past with the present moment. The cosmic microwave background radiation, CMB, is an isotropic glow that fills all of space with microwaves left over from the Big Bang. It acts as a cosmic blueprint, its minute temperature fluctuations marking out the seeds of what would eventually become galaxy clusters. These variations are so slight, just 1 part in 100,000, but they are enough to initiate gravitational processes that will shape entire universes. Remarkably, these tiny ripples were imprinted just 380,000 years after the Big Bang, when the universe was still cooling from its fiery birth. The CMB's influence is not static. It subtly nudges matter into denser concentrations over billions of years, a process that can be likened to a cosmic sculptor patiently chiseling away at raw stone. This ancient radiation continues to guide the assembly of galaxy clusters today. Galaxy clusters form through gravitational interactions between dark matter and ordinary baryonic matter, but it is the CMB's initial density perturbations that set this process in motion. These perturbations are not uniform. Some regions have slightly more mass than others, causing them to attract nearby material over time. In a sense, these variations act as gravitational seeds, around which galaxies and galaxy clusters eventually coalesce. The distribution of matter in the early universe was so even that without such minute variations, our cosmos might have remained an undifferentiated expanse of gas and dust. This delicate balance between uniformity and fluctuation is what allows for complexity to emerge from simplicity. Today, these primordial imprints can be observed as vast structures, spanning millions of light years, each cluster a testament to the initial conditions set in the first instance after the Big Bang. The CMB's influence extends far beyond just the early universe. It shapes galaxy clusters over cosmic time by affecting their growth and dynamics. As matter falls into these nascent structures, it heats up due to friction and gravitational compression, forming the X-ray emitting hot gas that is a hallmark of mature galaxy clusters. This process, known as hierarchical clustering, means that smaller clumps merge to form larger ones, each step amplifying the initial density variations from the CMB. Interestingly, this growth process can be interrupted by phenomena such as supernova feedback or active galactic nuclei, which inject energy back into the system and prevent it from collapsing too quickly. The interplay between these factors determines whether a cluster will grow into an enormous cosmic structure like the Coma cluster or remain a smaller collection of galaxies. Intriguingly, While the CMB's effects are most pronounced in the early universe, its influence persists throughout cosmic history. As galaxy clusters mature, they continue to be sculpted by the gravitational pull of surrounding dark matter halos, which owe their existence to those initial density perturbations. Over billions of years, these structures grow more massive and complex, eventually becoming the largest gravitationally bound objects in the universe. The CMB's role here is subtle but profound. It sets the stage for cosmic evolution by dictating where matter will coalesce and form galaxies, stars, and ultimately life-supporting planets. Without this ancient radiation, our galaxy might never have formed, and we would not be here to contemplate its influence. One of the most surprising aspects of CMB's role in cluster formation is how it connects microscopic processes with macroscopic structures. The initial density variations that seed galaxy clusters are rooted in quantum fluctuations from the earliest moments of the universe. These tiny perturbations, on scales smaller than an atom, were stretched to cosmic proportions by inflation, leading to the large-scale structure we observe today. This connection between the very small and the very large highlights a fundamental truth about our universe. Processes that operate at different scales are deeply intertwined. The same quantum fields that describe particles like electrons also govern the distribution of matter on galactic and supergalactic scales. This interplay suggests that the universe is governed by a single, unified set of rules that apply across all scales. As we look deeper into space, we are essentially looking back in time, peering at different epochs of cosmic history. Each galaxy cluster we observe represents a snapshot of its formation process, which began with the CMB's density perturbations. By studying these clusters, astronomers can trace their growth and evolution over billions of years, providing insights into how galaxies assemble and interact within larger structures. This ongoing research not only enhances our understanding of cosmic evolution, but also underscores the enduring legacy of the Big Bang. The CMB's imprint on galaxy clusters is a reminder that even the faintest echoes from the universe's infancy have profound consequences for its future. It is through these subtle variations that we can piece together the grand narrative of how structure emerged from the primordial soup of the early universe. In an unremarkable patch of sky above the Earth's equator, the cosmic microwave background radiation, CMB, appears as a nearly uniform glow, its temperature varying by less than 0.001 degrees Celsius across vast distances. This smoothness is not just a characteristic of the early universe. It is the very foundation upon which all cosmic structures were built. Yet, within this uniformity lies the seed of chaos, tiny fluctuations that, over billions of years, would blossom into galaxies and clusters. These variations in temperature, on the order of microkelvins, are so subtle they seem insignificant at first glance. However, consider this. These minuscule differences represent the initial conditions from which all cosmic diversity emerged. It's akin to the slight perturbations in a calm pond that can grow into vast ripples over time. The uniformity itself is a testament not just to the Big Bang, but also to the extraordinary sensitivity of our instruments, capable of detecting temperature variations far smaller than any human could perceive. As we fast forward through cosmic history, these subtle imbalances amplify exponentially. Gravity acts as a sculptor, pulling denser regions together into stars and galaxies, while leaving less dense areas relatively empty. This process is known as gravitational instability, where the slight overdensity in one region leads to an ever-growing disparity. The contrast between the early uniformity of the CMB and the chaotic structures we observe today underscores the profound transformation that occurs across cosmic timescales. The universe's initial smoothness is not just a relic of its birth. It also speaks to the simplicity from which complexity arises. This simplicity, however, belies the intricate processes at play. The same laws of physics that govern these tiny fluctuations are responsible for the formation of every star and planet in existence. It's a reminder that order can lead to disorder, and that even in the most homogeneous environments, seeds of diversity lie dormant. In our current epoch, galaxies like the Milky Way trace back to those very initial temperature differences. The first stars ignited roughly 100 million years after the Big Bang, their birthplaces marked by regions where matter was slightly more concentrated than average. This process continued for billions of years, with each generation of stars contributing to the enrichment and further differentiation of space through supernovae explosions and planetary formation. Each galaxy is a unique expression of those initial conditions. The contrast between the CMB's uniformity and the chaotic structures that emerge from it also hints at the universe's future. As time progresses, galaxies will continue to collide and merge, eventually forming giant elliptical galaxies or even superclusters. Yet, in this grand cosmic dance, the fundamental principle remains unchanged. The initial conditions laid out by those early temperature fluctuations guide every subsequent stage of evolution. This continuity across billions of years is a profound reminder of how deeply interconnected all elements of the cosmos truly are. The contrast between the uniformity of the cosmic microwave background radiation and the intricate web of galaxies, nebulae, and dark matter that fills the universe today is a stark reminder of how delicate initial conditions can shape an entire cosmos. This cosmic evolution is not merely a linear progression, but a complex interplay of forces acting on minute variations. In regions where the density was just slightly higher than average, gravity gradually pulled more material together, accelerating this concentration and eventually forming stars and galaxies. These nascent structures further attracted nearby matter, leading to the formation of galaxy clusters and superclusters, vast assemblages of galaxies held together by gravitational forces. Remarkably, despite the immense diversity of these formations, they all trace back to those minute temperature differences in the CMB. The distribution of mass in the universe is not random, but follows a pattern rooted in quantum fluctuations from the earliest moments after the Big Bang. These tiny irregularities were stretched across the cosmos by cosmic inflation, setting the stage for the formation of stars and galaxies. Each galaxy represents a unique solution to the equations of gravity, influenced by its specific initial conditions. The journey from uniformity to complexity is not just a physical transformation, but also one governed by probabilities and statistical mechanics. In some regions, the density fluctuations led to the rapid collapse of matter, forming dense cores that ignited into stars almost immediately. Elsewhere, these variations were less pronounced, leading to more gradual processes over cosmic timescales. This intricate dance of formation and evolution is a testament to the universe's ability to create order from initial simplicity, yet it also highlights how sensitive this process is to minute differences in starting points. Every star, galaxy, or black hole that exists today owes its existence to those subtle variations in temperature and density from the early universe. This interplay between uniformity and chaos continues even now, as we observe galaxies colliding and merging into larger structures, hinting at an ongoing process of cosmic reorganization. In the first 380,000 years following the Big Bang, the universe was an opaque plasma where light could not travel freely. Within this dense soup of particles, photons constantly scattered off free electrons, a process that now seems to have paused. Yet, it was precisely these collisions that set the stage for the cosmos as we know it today. Each photon in the cosmic microwave background, CMB, has traveled an average distance of about 14 billion light-years since the epoch of recombination, when electrons and protons combined into neutral atoms. This transition allowed photons to travel unimpeded across space, creating a snapshot of the early universe. Remarkably, these photons now fill every cubic centimeter of space with microwave radiation, their journey stretching back to an era before stars or galaxies formed. Imagine for a moment that you could witness this process directly. Countless particles dancing in an electromagnetic waltz, each collision marking time's passage. At its peak, the universe was so dense that it would take a photon 10 million years just to travel 1 meter. This density is comparable to water, but on scales far grander than any ocean or lake on Earth. As the universe expanded and cooled, hydrogen atoms formed, finally allowing photons to escape their long imprisonment. The sudden release of light from this recombination era is akin to a cosmic flashbulb illuminating the infant cosmos. Yet, even though this moment was incredibly brief in the grand scheme of time, it set the initial conditions for all future structures in the universe. After recombination, the CMB photons continued their journey through expanding space, stretching into longer wavelengths and cooling further. Today, these ancient photons are a mere 2.725 Kelvin above absolute zero, a temperature so cold that it approaches the theoretical limit of existence itself. The uniformity of this radiation across the sky suggests an early universe that was extraordinarily smooth, with only tiny fluctuations in density that would eventually grow into galaxies and clusters. Intriguingly, these same photons that once scattered off free electrons now pass through Earth's atmosphere without significant interaction. They provide a unique window back to when the universe became transparent, offering astronomers a glimpse of the earliest moments of cosmic history. This light, born from a time before stars, continues its journey, unaltered by the intervening eons, carrying with it the echoes of creation itself. The photons that constitute the cosmic microwave background CMB, are not static entities. They are in constant motion, traveling at the speed of light since their release at recombination. Each photon has been on a journey for nearly 13.8 billion years, yet its path is far from straightforward. As it moves through space, it encounters subtle variations in gravitational fields caused by large-scale structures like galaxy clusters and superclusters. These interactions cause the photons to follow curved trajectories, a phenomenon known as gravitational lensing. This effect slightly distorts their paths, sometimes even causing them to cluster together or disperse more widely than would otherwise be expected. Despite these minor perturbations, the overall uniformity of the CMB remains astonishingly consistent across vast distances. The temperature differences between any 2 points in the sky are minuscule, less than 1 part in 100,000. But these tiny variations contain profound information about the early universe's composition and structure. For instance, regions that were slightly more dense than average would eventually become the seeds for galaxy formation, while less dense areas would remain relatively empty. This delicate balance is a testament to the precision of physical laws governing the cosmos from its earliest moments. Moreover, these fluctuations have allowed cosmologists to map out the universe's history with remarkable accuracy, revealing how it evolved over billions of years. The CMB serves as both a fossil and a blueprint for understanding our cosmic origins and future evolution. In the far reaches of the future, long after the stars have dimmed and galaxies have scattered, the cosmic microwave background radiation, CMB, will continue to echo through the cosmos. This ancient light, born just 380,000 years after the Big Bang, will be absorbed and re-radiated by distant galaxies. These galaxies, now billions of years older than our own, will have transformed from their youthful spiral and elliptical forms into amorphous clouds of stellar remnants. The CMB's energy will be diluted as it interacts with these aging structures, stretching its wavelength to even longer microwave frequencies. Imagine a galaxy in the distant future that has consumed all its neighbor galaxies, forming an immense supercluster. Within this vast structure, the CMB photons will encounter interstellar dust and gas clouds. These particles, which are remnants of ancient stars, absorb and then re-emit the CMB's energy at longer wavelengths. This process is a cosmic recycling mechanism, where light from the Big Bang continues to be processed through stellar evolution cycles over billions more years. Yet, despite this continuous interaction, the overall intensity of the CMB diminishes with each absorption and emission cycle. The temperature of the CMB, now slightly cooler than it was in our era due to the expansion of space itself, will continue to drop as time progresses. At a current average of 2.7 Kelvin above absolute zero, this radiation is already among the coldest phenomena in the universe. In the far future, however, each photon's journey through intergalactic and galactic dust clouds will further reduce its energy, causing it to stretch into even longer wavelengths than those we can detect today. This process of redshifting over such vast timescales is a testament to the sheer immensity of cosmic time. Consider that in this distant future, our current understanding of galaxies as active, star-forming systems will be long forgotten. Instead, these superclusters will consist mainly of dark matter and stellar remnants, black holes, neutron stars, and cold gas clouds. These structures will absorb CMB photons over billions more years, a process that stretches the wavelengths of light to such an extent that it becomes nearly undetectable by any technology we could imagine today. This absorption and re-emission cycle is not only a cooling effect, but also a means by which information from the early universe continues its journey through time. In this distant epoch, the CMB will no longer be uniform across space as it is now. Instead, it will appear more structured due to interactions with these galactic remnants. Each photon's path will become increasingly convoluted, weaving through interstellar dust and gas clouds, altering its trajectory and energy level. This complexity adds a layer of intricacy to the CMB's pattern that we cannot see today. As each galaxy absorbs and re-emits this ancient light, it subtly imprints itself on the cosmic microwave background, creating a faint, ever-changing map of stellar evolution across billions of years. The final fate of the CMB lies in its eventual absorption by black holes scattered throughout these superclusters. These singularities will continue to grow as they consume surrounding matter and energy, including the re-radiated light from the early universe. In this way, the information contained within the CMB will be locked away forever, becoming a permanent part of the structure of space itself. Despite this eventual fate, the CMB's journey through time serves as a bridge between the infancy of our cosmos and its distant future, offering a continuous thread that links all epochs together in the grand tapestry of cosmic history. Beneath the noiseless hum of cosmic microwave background, CMB, radiation lies an intricate pattern that our senses alone cannot perceive, the polarization within this ancient light. This subtle alignment of photons reveals far more than meets the eye. It serves as a window into the universe's earliest moments, offering insights into gravitational waves from inflation, a phenomenon so distant in time and space that it defies immediate comprehension. To detect these minuscule polarizations, scientists use specialized instruments like the BICEP-2 telescope stationed at the South Pole. The extreme cold of this location is crucial. The icy landscape provides a stable environment free from atmospheric interference. Here, detectors are calibrated to pick up minute variations in temperature and polarization across vast distances. These fluctuations are so slight that they challenge our ability to grasp their significance on human scales. Yet, within these tiny distortions lie clues about how space itself stretched at unimaginable speeds during the universe's infancy. Imagine if you could see the CMB like a quilt of light patterns spread across the sky. Each thread represents a photon's orientation, woven together in a complex dance. However, this metaphor falls short when we consider that these threads are not static, but dynamic, continuously shifting as space expands and contracts on scales far beyond human perception. The polarization data collected by BICEP-2, for instance, indicates a unique twist in the fabric of spacetime, a relic from inflationary cosmology. This insight is akin to finding a needle buried under centuries of sediment. It demands meticulous analysis and profound patience. Gravitational waves, predicted by Einstein's theory of general relativity, manifest as ripples in space-time, caused by violent cosmic events like neutron-star collisions or black hole mergers. Yet, the gravitational waves detected through CMB polarization trace their origins to an epoch when the universe was less than a trillionth of a second old. This discovery reveals that even our most sophisticated instruments can only scratch the surface of understanding such ancient phenomena. The data collected is not just about distant events, but also about the fundamental nature of reality itself, challenging us to reconsider what we know about the cosmos. The polarization pattern detected by these instruments provides evidence for quantum fluctuations during inflation, an era when space expanded exponentially faster than light could travel. This process imbues the universe with an inherent unpredictability at its most microscopic level. It is as if the universe, in its earliest moments, played a game of chance that ultimately shaped everything we see today. This connection between the infinitesimal and the cosmic underscores how profoundly interconnected all aspects of existence truly are. Scientists continue to refine their methods for detecting these minute polarizations, pushing the boundaries of what can be observed from Earth's surface and beyond. Newer instruments like the Simons Observatory in Chile promise even greater sensitivity. These advancements will allow us to probe deeper into the mysteries of inflation and its aftermath, potentially uncovering further clues about the universe's birth. Each improvement brings us closer to unraveling one of nature's most profound puzzles. How did this vast cosmos emerge from a point infinitely smaller than an atom? The temperature anisotropies within the cosmic microwave background radiation, CMB, are minute variations in temperature that can be measured to extraordinary precision, differences of just 100 microkelvin across vast expanses of space. These fluctuations, though imperceptibly small, contain a wealth of information about the early universe's structure and evolution. What is perhaps most remarkable is how these tiny differences correlate with the distribution of dark matter in our cosmos. Dark matter, which neither emits nor absorbs light, forms an invisible scaffolding upon which galaxies and clusters are built. The imprint of this unseen substance is etched into the CMB, a relic from just 380,000 years after the Big Bang. Consider that for every atom we can see in the night sky, there are approximately 5 times as many particles of dark matter. This shadowy presence exerts gravitational influence without interacting with electromagnetic radiation, making it invisible to conventional telescopes. Yet, through the subtle temperature variations in the CMB, scientists have mapped its distribution across billions of light years. These maps reveal regions where dark matter is more densely packed, areas that would later become the seeds for galaxy clusters and superclusters. The universe's first light is thus not only a snapshot of the infant cosmos, but also a blueprint for cosmic architecture. The patterns in these temperature anisotropies are like fingerprints left by the earliest structures of our universe. They encode information about how galaxies formed, where matter clumped together, and even the dynamics of cosmic inflation. To observe such minute fluctuations is akin to reading the fine print on a document written in the most ancient script known, the birth certificate of the cosmos. Each speckle of warmer or cooler radiation in these maps represents a region where gravity was slightly stronger or weaker at the dawn of time, setting off cascades of events that would eventually lead to the formation of stars and galaxies. In our modern universe, these regions correspond to vast cosmic voids and dense galactic clusters. The CMB's temperature variations are like the seeds of complexity in an otherwise uniform field. As we observe these patterns today, we are witnessing a direct link between quantum fluctuations at the Planck scale, events smaller than the nucleus of an atom, and structures that span hundreds of millions of light years. This connection defies intuition. How can events so tiny have such profound effects on scales so vast? Yet, it is precisely this intricate dance between the microcosm and the macrocosm that defines our universe's architecture. The CMB's temperature anisotropies also hold clues about the nature of dark matter itself. By analyzing the way light from these ancient epochs bends around massive objects, scientists can infer the presence and distribution of unseen material. This technique, known as gravitational lensing, reveals a web-like structure that dark matter forms across cosmic distances. The patterns observed in the CMB suggest that dark matter particles interact very weakly with normal matter, making them nearly impossible to detect directly. However, their influence is unmistakable. They sculpt galaxies and provide the gravitational glue that holds clusters of galaxies together. Understanding these connections between CMB temperature anisotropies and dark matter distribution offers insights into the fundamental forces governing our universe. It underscores how the universe's earliest moments laid down the blueprint for its future development. As we peer further back in time, through the lens of ancient radiation, we uncover not just the history of galaxies, but also the invisible threads that weave together the cosmic tapestry. This delicate balance between what is seen and unseen continues to shape the cosmos, from the smallest subatomic particles to the largest structures in space. At approximately 380,000 years after the Big Bang, cosmic recombination occurred, a pivotal event where protons and electrons combined to form neutral hydrogen atoms for the first time. This process allowed photons to travel freely through space, unimpeded by the dense plasma that had previously scattered them. Each of these photons has been traveling across the universe ever since, carrying with it the imprint of conditions in the early cosmos. For an observer today, this light appears as the cosmic microwave background radiation, CMB, a nearly uniform glow that permeates all directions in space. The significance of cosmic recombination lies not just in the release of photons, but also in its role in shaping our understanding of the universe's history. Before this epoch, the universe was an opaque fog where no light could pass through without being scattered or absorbed. The sudden transparency allowed for the first true images of the cosmos to emerge, like a veil lifting over a newborn child. This event marks the point when the universe became transparent enough for us to observe and measure its early conditions today, offering insights into the Big Bang's immediate aftermath. In this era, the universe was vast but far from static. As atoms formed, gravity began to act on these tiny particles, gradually pulling them together. The subtle variations in density that existed before recombination became seeds for future galaxies and clusters of galaxies. These minute fluctuations, differences as small as 1 part in 100,000, are responsible for the structure we see today across billions of light years. Imagine if you could observe the universe at this moment. It would appear smooth, but with the faintest ripples, each containing the potential to become cosmic wonders. The CMB photons that reached us now are remnants from an era when the universe was a mere child in cosmic terms. They have traversed 13.8 billion years of expansion and cooling to reach Earth. Each photon's journey is unique, yet they collectively form a coherent picture of what the infant universe looked like. The temperature variations in this radiation, measured at a level less than 1 part per million across different parts of the sky, reveal the initial conditions that gave rise to cosmic structure. These fluctuations are so small and precise that detecting them required instruments on satellites like COBE and WMAP, which captured data with an accuracy that would have been unimaginable just decades ago. As these photons continue their journey through space, they interact with matter in ways both subtle and profound. In the vicinity of Earth, for example, some CMB radiation passes through our planet's upper atmosphere, where it interacts with atoms and molecules, subtly altering its path and energy. This interaction provides a glimpse into how cosmic phenomena can influence local environments on much smaller scales. The photons from the Big Bang thus connect the largest structures in the universe to the smallest processes right here on Earth. The CMB we observe today is not static. It changes as the universe evolves, even if very slowly. As time progresses and the universe continues to expand, these ancient photons will become even more diffuse and fainter. In billions of years, when galaxies have ceased their formation and stars no longer shine brightly, the CMB will be one of the few remaining traces of the Big Bang's energy. It will persist, a silent witness to our cosmic origins, long after other signs of life and structure in the universe have faded away. Each photon carries with it a story from an age when the cosmos was young and everything was possible. Within the Earth's ionosphere, GPS satellites orbit at an altitude of about 20,200 kilometers, where they navigate through regions influenced by both gravity and magnetic fields. The precision required for these satellites to pinpoint locations on our planet's surface is achieved partly thanks to the cosmic microwave background radiation, CMB. This radiation acts as a reference point, ensuring that atomic clocks aboard each satellite maintain consistent time. The stability of CMB's temperature provides an unparalleled benchmark. Imagine if we could replace the CMB with another cosmic phenomenon as our timing standard. While other celestial events might offer similar consistency, none come close to the uniformity and ubiquity of the CMB. It is a relic from 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely across space. This ancient radiation bathes us in microwave frequencies that vary by less than 1 part in 10,000, providing an extraordinarily stable reference point. Atomic clocks aboard GPS satellites are accurate to within a billionth of a second per day. This level of precision is crucial for applications ranging from global navigation to precise timekeeping in financial transactions and telecommunications. The CMB's role here is not merely a technical convenience, but a profound link between deep space phenomena and our daily lives on Earth. Without this cosmic reference, the accuracy of GPS systems would degrade significantly over relatively short periods. To understand why the CMB serves as such an effective timing tool, consider that atomic clocks measure time based on the natural resonance frequency of atoms. Variations in these frequencies can be influenced by gravitational fields or temperature changes. The consistency of the CMB's microwaves ensures that atomic oscillations remain synchronized across vast distances and varying conditions. This is critical because Earth's gravity varies slightly from place to place, affecting local clocks. Intriguingly, this reliance on the CMB underscores humanity's deep connection with cosmological scales. While we use GPS for mundane purposes like driving directions or tracking shipments, these systems are grounded in some of the universe's oldest and most stable features. The same radiation that illuminated the early cosmos now helps us pinpoint locations on Earth with incredible accuracy. This interplay between the microscopic processes within atomic clocks and the macroscopic phenomena of the universe is a testament to physics' underlying unity. Moreover, this dependency on CMB for precise timing reveals how finely tuned our technological infrastructure has become. The stability of the microwave background radiation ensures that every GPS satellite can agree on the exact same time, no matter their position in orbit or local gravitational environment. This synchronization underpins not just navigation, but also critical applications like global positioning systems for air traffic control and emergency response services. In essence, the CMB serves as a cosmic timekeeper, its ancient light helping to synchronize the clocks that guide our modern world. The precision of GPS timing, calibrated by the cosmic microwave background radiation, CMB, is so fine-tuned that it allows for real-time adjustments based on the movement of satellites through Earth's gravitational field. As these satellites orbit the planet, they experience slight variations in gravity due to Earth's non-uniform mass distribution. Think of the dense concentration of metals beneath Africa or the lighter regions elsewhere. These gravitational fluctuations can cause atomic clocks to tick at slightly different rates, a phenomenon known as gravitational time dilation, predicted by Einstein's theory of relativity. To counteract this effect and maintain synchronization, engineers have introduced corrections into GPS algorithms that account for these minute changes. The CMB provides an unchanging backdrop against which such adjustments are made. Without it, the discrepancies between satellite clocks could accumulate rapidly, leading to navigational errors that would render GPS systems unreliable within hours. This continuous calibration is crucial because the stakes of precision timing in our interconnected world are extraordinarily high. Imagine aircraft collisions or lost shipments due to inaccurate location data. Remarkably, this system relies on a signal from nearly 14 billion years ago, when the universe was just beginning to cool and form into the structure we recognize today. The CMB's consistent temperature profile acts as an anchor in time, allowing for precise atomic clock synchronization across thousands of kilometers above Earth's surface. This interplay between ancient cosmology and contemporary technology is a marvel of modern science. Each photon from the CMB that reaches our satellites has traveled through the vastness of space since shortly after the Big Bang. These photons now help ensure that the time kept by atomic clocks aboard GPS satellites remains in perfect sync, allowing for accurate navigation here on Earth. This process exemplifies how deeply connected we are to the cosmos. Even the most advanced technologies owe their precision to echoes from the universe's infancy. Within the cosmic microwave background radiation, CMB, lie subtle acoustic peaks that reveal the geometry of our universe's infancy. These are not sounds in the conventional sense, but rather temperature fluctuations that correspond to the pressure waves from the Big Bang's aftermath. Each peak represents a crest or trough in these primordial waves, akin to ripples on a pond disturbed by a pebble. The most pronounced peak indicates the size of the observable universe at the time when photons could finally travel freely, marking the end of the cosmic dark ages. Remarkably, these patterns are not random noise, but structured harmonics that reflect the shape and curvature of space itself at the earliest moments after the Big Bang. It's akin to hearing a distant echo in an enclosed room. The interval between each reverberation tells you about the size of the chamber. In this case, the intervals between CMB peaks inform cosmologists about the universe's geometry, whether it is flat, open, or closed. This precision allows scientists to measure deviations from perfect uniformity with a resolution finer than 1 part in 100,000. The second peak in particular provides critical information regarding baryonic matter distribution at that epoch. Baryons are the particles of which we and everything else are made, protons and neutrons. The amplitude of this second peak correlates directly with the density of these building blocks during cosmic recombination. This is a moment when light began its journey through space, unimpeded for the first time. It's remarkable to consider that our very existence owes itself to these minute variations in temperature, which ultimately seed galaxies and stars. The third acoustic peak offers insights into the universe's content beyond just baryons. It tells us about dark matter. This invisible substance, comprising roughly 27% of the cosmos, does not interact with light, but exerts gravitational influence on visible matter. The structure imprinted by dark matter enhances the oscillations in the CMB radiation, amplifying these peaks. It's a curious phenomenon. Though we cannot see or touch this mysterious form of matter, its effects are etched into the very fabric of the universe's early history. Each acoustic peak in the CMB spectrum corresponds to a specific scale factor related to the size of fluctuations at the time cosmic recombination occurred. These scales can be directly translated into physical dimensions, ranging from sizes comparable to our solar system up to those exceeding thousands of light years. This allows astronomers not only to study the large-scale structure of the universe, but also to infer fundamental parameters like the Hubble constant and the age of the cosmos. The precision with which these patterns are measured is truly astonishing, revealing a level of uniformity that defies expectation, given how chaotic conditions must have been just moments after the Big Bang. At human scale, it's challenging to grasp the enormity of what we observe in the CMB. Each fluctuation corresponds to regions of space that were once separated by distances far greater than our observable universe now spans. Yet, these minute temperature differences hold the blueprint for the cosmos as we know it today, galaxies, stars, and planets included. The CMB acts as a cosmic fossil record, preserving evidence of how quantum fluctuations inflated into the vast structures that fill space. In an era billions of years from now, long after galaxies have merged into vast clusters and the universe has stretched to unimaginable distances, the cosmic microwave background radiation, CMB, will persist as a relic of our origins. This ancient light, born in the first moments of the cosmos, is now a diffuse glow stretching across trillions of light years. As space expands, the wavelength of these photons lengthens, shifting into lower frequencies. The CMB's temperature has already cooled from an initial 3000 Kelvin to its current minus 270 degrees Celsius. But in the future, this radiation will grow even colder and less intense. This cooling is a consequence of the universe's relentless expansion. Every billion years, the space between galaxies increases, stretching the CMB's wavelengths further. This process, known as redshift, means that the light from the early universe becomes ever more diluted. By comparison, if we were to listen to this cosmic hum today, it would be akin to tuning a radio far outside its range, where only static remains. Yet even this faint signal carries profound information about our origins. In this distant future, these photons will have stretched so much that they may no longer be detectable in the microwave spectrum. The CMB's journey through time is intertwined with the formation of galaxies and the evolution of cosmic structures. As more galaxies merge under gravity's influence, vast clusters form, each containing hundreds to thousands of galaxies. This process, which has been ongoing for billions of years, will continue, creating larger and denser regions in space. These mergers are a natural consequence of gravitational attraction, but they also affect the CMB's distribution. The light that once filled every corner of the early universe now finds itself subtly altered by the gravitational lensing caused by these massive structures. This lensing effect bends the path of photons, causing them to take slightly longer journeys through space. Imagine for a moment standing in a vast auditorium where each seat represents a galaxy. Over time, seats close together begin to merge into larger clusters. As this happens, the light from the walls, the CMB, bends and stretches around these new formations. The light that once filled the room evenly now finds itself dimmer and more diffuse in some areas due to the gravitational influence of nearby clusters. This process not only changes how we might observe the universe, but also provides a unique perspective on how space itself evolves over time. In this distant future, the CMB will be so redshifted that it may no longer appear as visible light or even infrared radiation. Instead, it could shift into radio waves, becoming undetectable to conventional telescopes without advanced instrumentation. The universe's expansion is relentless, and with each passing billion years, more of the CMB's energy is stretched away from us. This transformation mirrors how our perception of time changes as we age. Just as childhood seems to stretch endlessly while old age feels fleeting, so too does the CMB's light become increasingly distant in both space and time. Yet despite this future dimming, the CMB remains a constant reminder of the universe's origins. It is a snapshot of what was once an intensely hot plasma, before the first atoms formed and light could travel freely across the cosmos. As more galaxies merge and cosmic structures grow, the CMB's influence on our understanding of the universe will diminish in intensity, but not in significance. This ancient radiation continues to illuminate the fundamental nature of space itself, a testament to the unifying force that connects all points in the expanding universe. At an elevation of approximately 30 kilometers above sea level, the air is thin and frigid, offering a unique vantage point for detecting the cosmic microwave background radiation, CMB. Here, the atmosphere's density diminishes to about 1/10 that at ground level. The CMB permeates this space with remarkable uniformity, its temperature hovering at 2.73 Kelvin, just above absolute zero. This environment is far from hospitable. For a human standing here, the lack of oxygen would be immediately life-threatening without specialized gear. Yet, it's precisely in such thin air that instruments can detect the faint whispers of the Big Bang with unprecedented clarity. Imagine this. While the CMB fills every corner of space like an invisible fog, its signal is subtly altered as it interacts with particles in Earth's upper atmosphere. At 30 kilometers above sea level, these interactions are reduced to a minimum. It's akin to standing at the edge of a vast, quiet lake, where ripples from distant disturbances can be observed more clearly than near the shore where they dissipate and mix into the water. This altitude provides a clearer window for instruments to discern the tiny fluctuations in temperature that tell the story of our universe's origins. The thin atmosphere at this height also allows for unobstructed views across vast stretches of sky. Instruments positioned here can sweep the heavens with minimal interference from Earth's lower atmospheric layers. The cold, dry environment minimizes thermal noise, enhancing the sensitivity of detectors. For an observer, however, every breath would be a struggle against the thin air, as oxygen levels drop to about 3% of those at sea level. This stark contrast between the delicate balance needed for optimal CMB detection and the brutal challenge it poses to human endurance highlights the precarious relationship between scientific observation and our physical limitations. At this altitude, the night sky appears different from what one might see on Earth's surface. The stars are sharper and more numerous, their light less scattered by denser air. This clarity allows for better detection of faint signals like those in the CMB. Yet, despite the apparent simplicity, each photon detected is a relic from when the universe was just 380,000 years old, older than any star or galaxy we can currently observe directly. The photons have traveled an average distance of about 46 billion light-years to reach us here on Earth, having been stretched by the expansion of space over nearly 14 billion years. The cosmic microwave background radiation detected at this altitude is not only a remnant from the Big Bang, but also a crucial tool for understanding dark matter and energy. While we cannot see dark matter directly, its gravitational effects are inferred through the subtle distortions it causes in the CMB's temperature patterns. These slight variations indicate the presence of vast cosmic structures invisible to us. The thin air at 30 kilometers allows instruments to map these tiny fluctuations with precision, providing insights into the distribution and nature of dark matter throughout the universe. For a moment, let's consider what it would be like for someone to stand here, peering through the clear, cold void. The temperature is about -57 degrees Celsius, and every breath exhaled would freeze instantly in the thin air. Instruments designed to detect the CMB are far from the only equipment present. There might also be weather balloons or specialized aircraft conducting atmospheric research. Despite the harsh conditions, this elevation offers an unparalleled view of the cosmos. In this rarefied environment, where human survival is marginal, science thrives, capturing the faint echoes of creation itself in a way that would be impossible at sea level. In spectral analysis, astronomers decode the cosmic microwave background, CMB, radiation by observing how hydrogen atoms interact with this ancient light. Each atom absorbs and re-emits photons at specific frequencies, creating unique fingerprints, spectral lines, that tell us about the conditions of early space. These lines act like barcodes, revealing the density fluctuations that seeded galaxy formation. This method is particularly powerful because it allows scientists to map these minute variations across the entire sky with unprecedented precision. The hydrogen atom's spectral signatures are so distinct that they can pinpoint temperature differences as small as 100 microkelvin in a background averaging just 27 Kelvin. This level of detail is akin to detecting a single grain of sand on a beach stretching from New York to Los Angeles. These variations, while seemingly insignificant, hold the key to understanding how structures in our universe formed. Astronomers use these spectral lines not just to observe, but also to calculate distances and velocities within the early universe. By measuring redshifts, how much light is stretched as it travels through expanding space, they can infer the scale of the cosmos during its infancy. This technique, known as cosmological redshift, reveals that the hydrogen atoms we observe are remnants from a time when the universe was less than 400,000 years old. It's a paradoxical thought. In this early state, the universe was opaque and filled with dense plasma, yet it laid down patterns so fine they only become visible through the subtle shifts in spectral lines. As we delve deeper into these measurements, another fascinating aspect emerges: the role of dark matter. The hydrogen atom's spectral lines suggest that much of the structure seen in the CMB is influenced by invisible, non-baryonic particles. This unseen mass gravitationally tugs on ordinary matter, guiding it to form galaxies and clusters. Without this mysterious substance, the universe would be a smooth sea of gas with no stars or planets. In addition to mapping hydrogen atoms, astronomers also study polarized light from the CMB. Polarization occurs when photons interact with magnetic fields or gravitational waves, causing their electric fields to oscillate in specific directions. This polarization pattern provides clues about how energy was distributed across the universe's earliest moments. The alignment of these patterns across vast distances is a testament to the uniformity of the Big Bang's aftermath, where tiny quantum fluctuations grew into the seeds of galaxies. By combining data from hydrogen spectral lines and polarized light, researchers can create comprehensive maps that trace back to the cosmic dawn. These maps offer insights not only into the origins of our universe, but also into its future evolution. The same processes that formed galaxies billions of years ago continue today on a grander scale, as clusters merge into superclusters and galaxies drift apart due to dark energy's accelerating influence. Understanding these dynamics helps us appreciate how the universe will evolve over time, from its fiery birth to its distant, cold end. Hydrogen spectral lines not only map the distribution of matter in the early universe, but also reveal clues about cosmic inflation, the rapid expansion that followed the Big Bang. During this brief epoch, the universe expanded exponentially faster than the speed of light, stretching quantum fluctuations into observable ripples on a cosmic scale. These ripples are imprinted in the CMB as temperature and density variations. When hydrogen atoms recombined after the plasma cooled, these ripples were frozen into place, creating the blueprint for future structures. The spectral lines we observe today act like time capsules, capturing this moment of inflationary expansion. This phenomenon defies our usual understanding of physics, where nothing can travel faster than light. Yet, during inflation, space itself expanded at an incomprehensible rate, allowing regions that are now billions of light years apart to have once been infinitesimally close. The spectral analysis of hydrogen atoms helps us quantify this expansion by measuring the precise wavelengths shifted due to cosmic redshift. Each shift in the wavelength corresponds to a specific moment in time, providing astronomers with a timeline for when and how these quantum fluctuations grew into macroscopic structures like galaxies and galaxy clusters. This process underscores the delicate balance between quantum mechanics and cosmology. At the smallest scales, quantum uncertainty laid the foundation for the universe's largest observable features. The precision required to detect these shifts is remarkable. Imagine tuning a radio dial to catch whispers from the dawn of time. Each spectral line represents an infinitesimal adjustment in frequency, yet collectively they paint a detailed picture of the early cosmos. This level of detail is what allows scientists to discern not just where matter was distributed, but how it evolved into the galaxies we see today. The hydrogen atom's spectral lines also offer insights into the cosmic web, the vast network of filaments and voids that crisscross the universe. These structures emerge from the primordial density variations, with denser regions attracting more matter through gravity, forming clusters and superclusters. As these structures grow, they influence the polarization patterns in the CMB, adding another layer of complexity to our understanding of cosmic evolution. The cosmic microwave background radiation, CMB, is remarkably uniform across the entire observable universe, varying by less than 1 part in 100,000. This consistency challenges our understanding of quantum fluctuations and cosmic inflation, suggesting that at the very beginning of time, the universe was extraordinarily smooth on a macroscopic scale. However, beneath this surface lies a microscopic level of complexity. The slight variations within the CMB trace back to quantum fluctuations in the early universe, imprints left by minute differences in energy density just after the Big Bang. These tiny deviations would later grow into the vast cosmic structures we see today: galaxies, clusters, and superclusters. The uniformity is both a mystery and a key to unlocking how our universe evolved from an infinitesimally small point to the expansive cosmos of today. Despite its near-uniform nature, the CMB bears subtle imprints that hint at profound processes in the early universe's quantum mechanics. These imprints are so minuscule they appear as statistical noise, yet they reveal a universe where particles and forces were entangled in ways we can only begin to comprehend. To visualize this, imagine taking an image of the entire sky with a camera sensitive enough to detect variations equivalent to 100 microkelvin across vast distances. This level of precision is required to capture these subtle fluctuations. These measurements offer insights into how quantum mechanics and gravity might have interacted at scales far smaller than those currently experimentally accessible on Earth. The uniformity of the CMB thus serves as a bridge between the macroscopic universe we observe and the microscopic world ruled by quantum laws. The theory of cosmic inflation posits that these initial quantum fluctuations expanded rapidly to become the seeds for galaxies and galaxy clusters. This rapid expansion smoothed out most irregularities, explaining why the CMB is so uniform on large scales. However, this smoothness also presents a paradox. If everything was expanding uniformly, how did such minute variations arise? The answer lies in quantum mechanics, a realm where uncertainty reigns supreme. Even during inflation, random quantum fluctuations occurred, leading to slight density differences that eventually coalesced into the structures we see today. This process is akin to stirring cream into coffee. Initially smooth, it eventually develops patterns as the cream diffuses unevenly through the liquid. In a universe expanding at an exponential rate, these minute variations were stretched out over cosmic scales. The CMB's uniformity across such vast distances also challenges our concept of time and space. The photons from the early universe have been traveling for approximately 13.8 billion years to reach us. As they journeyed through space, they interacted with matter and radiation, gradually cooling to their current temperature of about 27 Kelvin. Yet, despite this long journey, these ancient particles maintain a remarkable consistency in temperature and distribution. This uniformity suggests that the universe's initial conditions were extraordinarily fine-tuned for structure formation. The CMB thus stands as a testament not only to the Big Bang, but also to the intricate balance between quantum mechanics and cosmic dynamics at its inception. It is through this delicate interplay that galaxies, stars, and planets could eventually form. The process by which these tiny quantum fluctuations grew into macroscopic structures is known as gravitational instability. Gravity acted on the small density variations present in the CMB, causing denser regions to attract more matter and thus grow further. Over billions of years, this self-reinforcing cycle led to the formation of stars, galaxies, and ultimately life. The universe's initial smoothness was therefore a necessary condition for its complexity. Without it, these fluctuations would not have had room to grow into the rich tapestry of cosmic structures we observe today. This process highlights an unexpected connection between quantum mechanics and cosmology. What begins as random noise in a microscopic realm can shape entire galaxies on a cosmic scale. The CMB's uniformity provides a critical test for models of inflation, which suggest that this rapid expansion smoothed out most initial irregularities, but left behind specific patterns of temperature fluctuations. These patterns are known as acoustic peaks and serve as fingerprints of the early universe's geometry. By analyzing these peaks, scientists can infer properties such as the density of ordinary matter, and dark energy in the cosmos. The fact that we can measure these minute variations with such precision underscores how far our understanding of the universe has come. It is a reminder that even the most uniform phenomena contain hidden complexities, waiting to be uncovered through meticulous observation and analysis. This process continues as astronomers refine their instruments and models, seeking deeper insights into the origins and evolution of the cosmos. In the deep void between galaxies, the cosmic microwave background radiation, CMB, maintains its uniform temperature across every direction we can measure. This radiation is a relic of the universe's infancy, a snapshot captured 380,000 years after the Big Bang, when the cosmic plasma cooled enough for light to travel freely through space. At -270 degrees Celsius, it remains one of the coldest things in the universe, yet its existence defies simple explanation. It is not merely a leftover glow, but a testament to quantum fluctuations that seeded the cosmos with structure. These minute variations, imprinted at the beginning of time, have grown into galaxies and clusters over 13.8 billion years. Theoretical models suggest that before the Big Bang, space itself might have been in a state of eternal expansion and contraction, a cycle of cosmic epochs known as the ekpyrotic universe theory. In such scenarios, our observable universe could be just one bubble among many, each expanding from its own Big Bang moment. This perspective challenges the notion of a singular origin for time and space. Instead, it posits an infinite series of beginnings and ends, with our CMB representing only one snapshot in this vast cycle. Yet, despite these speculative frameworks, what we observe remains consistent, a nearly uniform glow that persists across billions of light years. At -270 degrees Celsius, the CMB radiation interacts with matter in ways that are both subtle and profound. This interaction is crucial for understanding how galaxies formed from primordial density fluctuations. As photons scatter off free electrons during recombination, they impart a slight but measurable effect on the polarization patterns within the CMB. These patterns encode information about the early universe's conditions, such as the distribution of dark matter and energy. The precision with which we can measure these effects is remarkable. Differences in temperature of less than 100 microkelvin across vast expanses reveal the intricate structure that eventually gave birth to stars and galaxies. In our human experience, temperatures near absolute zero are achieved only under controlled laboratory conditions on Earth. Yet here, in the vacuum of space, this cold persists without artificial intervention. The CMB's temperature approaches absolute zero, a state where quantum fluctuations become more pronounced, offering a window into the fundamental nature of matter and energy at cosmic scales. This environment, though seemingly inhospitable, is one of the most stable phenomena known to us. It serves as an anchor point for measuring time across the cosmos, providing a consistent reference frame for astronomers studying distant galaxies. The CMB's journey through space has not been static. It has evolved along with the expanding universe. As space itself stretches, so too do the wavelengths of the radiation emitted at the Big Bang. This phenomenon is known as redshift, the process by which light becomes longer in wavelength and cooler over time. Today, the once bright ultraviolet radiation from the early universe has been stretched into microwaves, a journey that began with temperatures far hotter than any star can muster. The photons traveling through space today are the same ones released 13.8 billion years ago, each carrying an imprint of its origin. Returning to the idea of -270 degrees Celsius and the omnipresent glow of the CMB, we find ourselves at the intersection of time and scale. This radiation not only fills every corner of the observable universe, but also connects us to a moment when space itself was rapidly cooling. It is as if each photon carries with it the memory of an event that shaped the cosmos, from its earliest moments to the present day. In this context, the CMB serves as both a witness and a participant in the ongoing story of the universe, one that stretches far beyond our lifetimes and comprehension. At -270 degrees Celsius, a whisper from the Big Bang fills every corner of space, its cold embrace enveloping us in the vastness of the universe. This journey through cosmic silence is now coming to an end. Thank you for being here with me tonight, drifting among the stars. If you enjoyed this voyage, do consider subscribing and leaving a like. Good night, and may the tranquility of the cosmos guide your dreams.